So waves can add up in crazy ways. This is called resonance. This is an applet. Here we have a wave generator, and you can change the frequency of the wave generator shaking this wire. And the wire shakes and it's connected to this post. Let's take a look at it. As you can see, most of the time we just get a lot of noise, but then every once in a while something crazy happens, and that's kind of interesting. We'll try to find the fundamental frequency here. Try to find it there. This is the fundamental frequency, just one big lump. The key equation: velocity is equal to frequency times wavelength. The velocity is the same no matter what the frequency. And here's the key: if the wavelength fits, it fits. And if the frequency is a whole number multiple of the fundamental frequency, we can get a standing wave. We can get a standing wave. This is the third mode of the standing wave. That's pretty cool because waves add up. See, here we have waves coming in from the right, the wave generator shaking that wire, and then waves bouncing off the post and coming in from the left, and they combine. And if the timing's right, you can get some standing waves. If the timing's right, which is key to remember when you're pushing your kid on the swing. Push, 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 push. Time those pushes right, and the amplitude can get bigger. And if you do it right, you can even knock over a bridge. This is a real picture that's from almost 100 years ago of the Tacoma Narrows Bridge that fell over due to resonance. It was a suspension bridge. See those vertical suspension cables? Those were the culprit. That's why it fell over. Here is a bird's eye view of a rock in a stream. The water flows past the rock. Water and wind are both fluids here. And then there are eddies. There are eddies downstream from the rock. The fluid is pushing off these eddies, some above, some below. They spiral off. Call it vortex shedding. As the wind passes those suspension cable, there's a vortex and a little push. If the vortex is thrown up, there's a push down. If the vortex is thrown down, there's a push up. And these small little pushes are pretty small. But if the timing's right, you can knock a bridge over due to resonance. Or think about shaking up and down a spring mass system. This works really good with a slinky and a tennis ball. You shake that thing back and forth, and we've already seen the equation for the frequency of the spring mass system. Here's the deal. If you shake it too fast, that's too fast. Shake it with too low a frequency, that's too low. But if you shake it, and you don't have to move your hand very far at all, just tiny little pushes at the right frequency, and the amplitude will get huge. When the frequency of the forced oscillation matches the natural frequency of the system, resonance, amplitude gets huge. Huge enough to break a drinking glass. Here's another video here. They thunk the glass, and as they thunk it, they listen to the natural frequency, the frequency that the glass wants to vibrate at. They record that, and then they pump it back on the glass. The frequency of the forced oscillations forced from the sound waves here, the frequency of the forced oscillations match the natural frequency of the glass, and it shatters. And that may be true for transverse waves, but does it work for longitudinal waves also? Yes, according to this diagram. Yes, according to this applet. See, the air molecules are moving back and forth, and we have nodes and antinodes. We have standing waves here, and if you don't believe me, Google Rubin's tube, and you can see here we have gas on fire in a tube with speakers on either end, and the right notes in the music make standing waves.